one final example before we wrap this up. And this is a preheated tower, as some of you would know who are in the cement industry. These preheated towers are very common, and they're very complicated structures, considering the fact that the equipment which runs through them is highly complicated, and there's a lot of different loading conditions. Now, let's say we wanted to do, we don't want to do a response spectrum analysis, but we wanted to do a time history analysis on this. Obviously, I personally prefer to do the response spectrum analysis in most cases, because they are much easier to deal with, and they create much less clutter. And the one response spectrum can actually cover dozens of time history analyses, because if you select a particular time history, you would need to be very careful, because it might not represent the full spectrum of that area. So theoretically also, you would need to at least consider maybe 20, 30 different time histories and ensure that they are equivalent to the response spectrum of your area and your site. And that's a very hard task, and also considering that doing a full time history analysis itself is quite challenging in many ways as well. But anyway, getting down to what we have at hand, what I've done is, so what we do is basically you start off with the time history function, so you can create and edit time functions and ground motions. So here I've created the El Centro North ground motion. Some of these ground motions are available on the internet, and if you modify and view that, you can see that this is it lasts for about 30 seconds, the shaking, and you can give it a name, and you can import it from a file and all that. And once you have that, you move on to your next step. And that next step is you go to your menu over here once again, and you go to this create, edit, load cases and combinations. And on the right hand side, you have dynamic load patterns. If you select that, you have the option, you can create a dynamic load pattern again over here. And to this load pattern, you can assign any time series. So we just created this time series of El Centro. So if you can create more than one. And over here, you give it a name, and then you assign a particular time series to it. And then you say that you want to assign this time series in the X direction. So let's say this earthquake is in the X direction. And you have the time series can be given some units and a scale factor. And this will constitute a ground motion excitation, if you will. You also have the option of time varying loads, so you can actually apply particular loads to particular joints if you want as well. But here we're going to do a ground motion excitation. And once you're done with that, then you go to this create and edit analysis cases, where you create this analysis case, and inside you can then select the dynamic load pattern which you just created. If you want to add, you could have created more than one, and these ones will be combined. And you need to tell it what integration method it will use. So you have the option of Newmark integration or Wilson integration, and you can also change the number of steps. So obviously the time series has a certain number of steps, but you can go beyond the time series. So for example, the earthquake lasted for about 30 seconds, but you might want to do the analysis for 40 seconds. So you can have a different number of time steps, and even you can have a different time interval as well to make your job or make the process simpler or whatever. Now, once we run the analysis, let me go to the top floor. This is the joint over here, and the ground has been shaking under the El Centro excitation. And if I were to go to the element joint output, and I select the response history, and over here, once again, the final result is shown. But if I select the response history, I can see the whole thing. And then what I can do is I can say plot to the file. And over here, since I did it in the X direction, I'm going to choose U1, and I'm going to say I want to see the displacement of this top column joint. And I say the units are millimeters, and I say OK. And when I do that, I can see that the excitation of the El Centro earthquake has created a maximum response of about 150 millimeters at the top. And then it started to come down, and this is where the earthquake ended, around 30 seconds. And after that, it's free vibration basically for until the damping will bring it down to 0. So at the top level, we have this deflection of about 150 millimeters in the plus direction. If I were to, for instance, go down to this floor and turn on my joints, for example, and let's see if I can zoom in and select this joint. So this is pretty close to the ground this time. The other one was at the top, and I go back to my joint element output. I select my history, turn it on, and say plot. And this time when we plot it, we will see it's a more violent shaking actually, because over here it's much stiffer near the base, and the smaller frequencies, or the higher frequencies I should say, the smaller periods play more of a role, but the overall amount of displacement is much smaller than the top floor, because it's very close to the ground floor. And you can see that it's been shaken more violently as far as the frequencies are concerned, but the total deflection is a lot lesser. So you can do analyses like these and satisfy your curiosity about how the structure is going to behave, and Comosys will help you do those kinds of things as well.